Welcome to Engineering Science in 3, and today we'll be taking a look at the February 2022 past exam paper, and the section that we'll be looking at is heat, which is question 5. Okay, so let's take a look at the question. So question 5.1 reads 5 kilograms of fuel is burned for 30 minutes in a factory. 45% of the heat from the combustion process was used to heat up 2.1 liters of oil from 32 degrees to 135 degrees. Hint, so this is very important, please concentrate on the hint. 1 liter of oil has a mass of 0.85 kilograms. So now in this question you will notice we have two substances. The first substance is a fuel, the second substance is oil. Okay, let's extract the given information. The first thing here you would notice is that you are given the mass. The mass of the fuel is 5 kilograms. Next thing you have the time. The time is 30 minutes. Okay, the time should not be in minutes. The correct SI unit for time is seconds. So we're going to convert from minutes to seconds, and to convert from minutes to seconds, we're going to multiply by 60. So we're going to say 30 times 60, and the time here is 1,800 seconds. The next thing you will notice is only 45% of the heat energy from the fuel to the oil is transferred. Therefore, we are given an efficiency, which is 45%. Next, you got 2.1 liters of oil. Okay, so if something is measured in liters, that quantity there is your volume. So 2.1 liters, and normally when we deal with volume, volume should not be in liters, volume should be in meters cubed. So for study purposes, if you have to convert any question from liters to meters cubed, we divide by 1,000, so it's 2.1 times 10 to the minus 3 cubic meters. The oil is heated from 32 degrees. When we see the keyword at or from, that there is your initial temperature, and the symbol for initial temperature is T1. And when it goes to or of, then that there is your final temperature, and the symbol is T2, 135 degrees. Okay, so let's look at the first question. It says determine the heat energy required for temperature change. Right, so if you remember now that the oil was being heated up from one temperature to another, so the heat energy that they're asking us to calculate is the one for the oil. Okay, so the heat energy is moving from the oil, from the fuel to the oil. So if I look at the given information that we have, we now find that we've got the mass of the fuel, we've got the time, all right, and we now know the temperature is changing from 32 to 135 degrees. So I need to find the heat energy that the oil is receiving. Since oil is a normal substance and a fuel, we're going to use M times C multiplied to T2 minus T1. Okay, the first thing I'm going to do is calculate the mass of the oil. Okay, and when I calculate the mass of the oil, remember we use the hint. 1 liter of oil is equal to 0.85 kilograms. So I'm going to take the number of liters of oil that we have and multiply by the mass. In this case, it is 2.1 multiplied to 0.85. Because they are measuring the mass of the oil in liters, we are going to leave the volume in liters. We are not going to use it in centimeters cubed. Alright, so we then find that the mass of the oil is 1.785 kilograms. Okay. So now we're going to substitute into my formula. Heat energy for oil is M times C multiplied to T2 minus T1. Alright, so my mass here is going to be 1.785, which I just calculated. This is the specific heat capacity for oil. Where do we find this? We find this on the information sheet. So if you go to your information sheet, which is after the formula page in your question paper, you will look the specific heat capacity of oil, and you will find the value there is 2000. T2, the final temperature is 135, the initial temperature is 32. Okay, you now find that the amount of heat energy that is needed for the temperature of the oil to change is 367,710 joules. Now let's take a look at the next question. The next question says determine the energy given off by the fuel. Okay, so as we can see in this diagram that I have alongside here, we have the fuel, which is burning. and as it burns, it transfers heat energy to the oil. Okay, so because the heat energy is moving from the fuel to the oil, the fuel side is considered the input side. Once the oil burns up and all the energy is used up by the oil, it gives off heat energy, and this is now considered the output side. However, we should take note that the fuel during the combustion process only works at 45%, while the oil, on the other hand, is able to burn up all of the heat energy and is therefore working at 100%. So my output side is working at 100%, while the input side is working at 45%. We are therefore now dealing with an efficiency. Okay, so as we can see from this question here, we know the mass of the fuel is 5 kilograms. We now know that the fuel is only burning for 45%. Right? So when we have efficiency, the formula which we use for efficiency is now going to be efficiency is output over input times 100%. Right? We have already determined now that the fuel side is the inputs and the oil side is the outputs. So my efficiency for the fuel, according to my question, is 45%. We now know the amount of heat energy from the previous question that the oil burns or gives up is 367,710. We are dividing by inputs because the fuel is the input side times 100%. The performance of a substance is measured by 100% in terms of efficiency. So now when I calculate, I have inputs is equal to 367,710 over 45% times 100%. When I do this correctly on the calculator, we now find that the amount of heat energy given off by the fuel is going to be 871,133.33 joules. Okay, our next question, we're going to calculate the heat value of the fuel. So when we are dealing with fuels, okay, as the fuel burns, we measure the amount of heat energy that the fuel produces or gives off by calculating what is known as the heat value. All right. So if I look at the given information that we have accumulated thus far, all right, we said we know the mass of the fuel is 5, the time for temperature change is 1,800 seconds. We now know that the fuel only gives off 45% of the heat energy. So this efficiency belongs to the fuel and not the oil, because the heat energy is moving from the fuel to the oil. Okay, we said the volume is staying in liters because the mass of the oil is measured in liters and not in cubic meters. Okay, in the previous question we calculated that the heat energy for the oil is 367,710 joules. Let's find the heat value for the fuel. Okay, when we are dealing with substances which are fuels, we use a new formula to calculate the heat energy. We know that the symbol for heat energy is Q. In the previous question, when we dealt with the oil, because oil was not a fuel, we took the mass and multiplied by the specific heat capacity and the temperature change. In this question, because we are dealing with a fuel, when you see the keyword fuel, the heat energy that is given off by a fuel is calculated as mass multiplied by the heat value. So let's substitute. Okay, we know the heat energy for the fuel is 817,133.33 joules. Okay, so we substituted that. And the mass of the fuel is 5 and the heat value is what we are trying to calculate. Okay, so if I make heat value the subject of the formula, I'm going to get 817,133.33 divided by 5, and the heat value for the fuel is now going to be 163,426.667 joules per kilogram. So the heat value is measured in joules per kilogram. That means for every 1 kilogram of fuel that is burnt, the heat energy given off is 163,426.667 kilograms. Okay, next question, let us determine the power given off by the fuel. Let's look at some basic information that we now know. We know that the amount of heat energy given off by the fuel, when it is working with an efficiency of 45%, is 871,133.33 joules. We now know that the fuel is burning for 30 minutes, and we said we are converting from minutes to seconds. We multiply by 60, so the total amount of time that the fuel is burning for is actually 1,800 seconds. So let's look at a formula we can use for power. So power measures the rates at which work is done. And we know that work done can convert to energy, which is why we are using power is equal to Q over T. So instead of saying power is equal to work done over time, we can now say power is equal to energy over time. In this case, the type of energy we are using is heat energy. And because we are calculating the power given off by the fuel, we are using the heat energy for the fuel. Right? So when I substitute into the formula, we now can see that the amount of heat energy given off by the fuel is 871,133.33 joules, and the time in seconds is 1,800. So the amount of power given off by the fuel is going to be 453.962 watts. Let's go to question 5.2, and this now deals with a new section in heat. We are now going to be looking at steam table calculations and how to calculate the heat energy for the different types of steam that is being produced. So question 5.2 reads that the dryness factor of 5 kilograms of wet steam is 0.90. Okay, so wet steam is steam that simply has water particles in it, right? This steam is generated at a boiler pressure of 3.4 megapascals. The pressure is very important to know and understand in this question, all right? Because this question deals with pressure that is measured in kilopascals on the steam table. So when we use the steam table, the pressure is measured in kilopascals and not in megapascals. So conversions are very important for this section, right? So if I look at what is given, I know the mass is going to be 5 kilograms. Okay, X represents the dryness factor, it's 0.90. P is my pressure, and here we said the pressure is in megapascals. As I just explained, we said on the steam table, the calculation is done using pressure in kilopascals. To convert from megapascals to pascals, we multiply by 1,000. So the pressure now becomes 3,400 kilopascals. Please make sure that you get the conversion for scientific notation correct. Okay, when we move from kilo to mega, okay, the factor is only moved by 8,000. Okay, this here is scientific notation. Right, so let's read question 5.1 or 5.2.1. It says calculate the specific enthalpy. So when we use the word enthalpy, we are referring to heat energy of the following. 5.2.1, the liquid at saturated temperature, which is HF. So as I explained, this is what we now refer to as a steam table. You will receive one of these in your exam papers. It normally comes as a booklet, or you can receive it in the question paper itself. So on the steam table, the first column is very important. This is your pressure. As you can see here, your pressure is in kilopascals. The next column that we have is HF, which is your liquid at saturated temperature. And as you would see here, you would notice that it is measured in kilojoules per kilograms. HFG is your evaporation enthalpy, kilojoules per kilograms, and Hg is your dry steam, kilojoules per kilogram. So it is very important to take note that the amount of heat energy that is generated on the steam table is measured in kilojoules per kilogram. That means the heat energy calculated here is measured for so many kilojoules for every 1 kilogram. So the heat energy on the steam table given off is only for 1 kilogram. Right, so what I'm going to do now is very important. You are going to go to your pressure column, which is here. We are going to look for this heat energy here, which is 3,400. As you can see, it is 3,400. I'm going to go across the line here, and I'm going to look for this column, which is HF. So when it is 3,400, the liquid enthalpy heat energy value is 1,042. So here you can see I have HF. The liquid enthalpy at saturated temperature is 1,042, but this is kilojoules per kilogram, which means this amount of heat energy or liquid enthalpy that is given off is only for 1 kilogram. According to my question, I do not have a mass of 1 kilogram, I have a mass of 5 kilograms. So what we are going to do next is take the value or the answer that I just had and multiply by the mass of 5. So when you have a mass greater than 1 kilograms, you always take the heat energy that is calculated for the steam and multiply by the mass. So the correct answer that we should now have for the heat energy of the liquid at saturated temperature should be 5,210 kilojoules. Right. The next one says calculates the specific enthalpy or heat energy of the following to dry the steam. Again, we are going to go here and look for the pressure of 3,400, and I'm going to draw across the line. What symbol am I looking for? I'm now looking for the symbol Hg, and that is in the last column here. So now this is the value that I have, which is 2082. Alright, so dry steam under this column is 2082, but again, this 2082 kilojoules per kilograms, this answer is only for 1 kilogram. My mass in the question is still 5 kilograms. So the next thing I'm going to do is take this 2802 and multiply by 5. And we should now get the amount of heat energy to dry the steam is 14,010 kilograms. Next question, I want to calculate the heat energy to evaporate the liquid. So the symbol we are now using for evaporation enthalpy is HFG, which is this column here. So I'm going to come down this column. I'm going to look again. The pressure is not 3.4 but 3,400 kilopascals. And this is where I have, if you have a ruler, you'll go straight across. And you'll now notice when I come here straight across from 3,400, I'm now going to be at this value here, which is 1,760. Okay, this column here represents HFG, alright, to evaporate the liquid. So again, as I said, it is 1,760 kilojoules per kilogram. Again, my mass is not 1, but my mass is 5. So I'm going to multiply by the mass. I'm going to say 1,760 times 5, which is 8,800 kilojoules. And we look at the final question. It says calculate the heat energy for the wet steam. Alright? So this is a formula you now need to remember. The formula that we use to calculate wet steam is H wet is going to be HF, which is your liquid enthalpy, plus X, which is your dryness factor, multiplied to HFG, which is your evaporation heat energy. And again, we must multiply to the mass when the mass of steam or water used is greater than 1 kilogram. In this case, the mass still remains as 5. So let's substitute into our values. So remember, these values obtained from the steam table. Okay, when I have a pressure of 3,400 and I go across the steam table and I look for HF, I can see here that the value is 1,042 plus 0.9. According to the question, the dryness fraction here is 0.9. And it is 0.9 multiplied to HFG, which is your evaporation enthalpy. So 3,400 I go across, my HFG or my evaporation heat energy is 1,760. Again, if I keep the answer as it is, I'm only going to get it for 1 kilogram. I now must multiply to the mass of 5 kilograms. Right? We should now get the total amount of heat energy for 5 kilograms of steam or wet steam is going to be 13,130 kilojoules. Thank you for watching today's lesson.